Good afternoon, everyone. Hello and welcome to week 11 of STEM Mode In. So thank you all for being on time. Thank you all for attending. Thank you all for your excitement. My name is Charlotte and I'm going to be your host again for this session. So welcome back if you've been before, and welcome to any newbies. We have the comments. If you have been here before, I'm sure you're used to it. We do have the comments, so do pop in the comments. We can see them, and our special guest can see your comments as well. So pop them in the comments. Any questions? Someone's already asked. Muna's already asked. Who likes engineering? So that's a great question to start with. So we're going to give it 2 or 3 minutes until we go live with the session. So feel free to grab a quick snack or grab a quick drink and see you shortly. Hi there for those that have just joined. Hello, there's some few more of you that have just joined. We are going to kick off in about a minute's time. Thanks for popping all your comments, having a nice little conversation there in the comments. We've already got a question about what today's session is going to be about. So sneak peek, we are focusing on engineering. It is kind of linked to Maryam Mirzakhani, who is our role model of this week, but we have a slightly different role model today that will be joining us. So watch this space, give it another minute or so. Pop some comments, any questions, any comments that you'd like for myself or our special guest, and we'll get going very, very shortly. Okay, let's get going. I think we've got enough people on for now. So thank you everyone for coming and joining on time, and welcome to STEM Mode in week 11. So as you can see, we are focusing on engineering in everyday objects with Mamta Singhal. So I'm going to bring her into the stream now. If you want to say a quick hello, Mamta.
Hi, everyone. Nice to see you. I love that. Who likes engineering and who likes maths? Oh my God, my 2 favorite subjects at school.
You see, we can see all your comments. We can see you having a little... So I'm going to move on to the next slide, and I'm going to say, Mamta, who are you and what do you do?
So I am a chartered design engineer. So I combined creativity and engineering and maths. And I've worked in industry, in the toy and the food industry, for about 18 years as a design engineer and an innovation scientist and all those kind of fun things. So there's loads of cool jobs out there for STEM people.
Who likes toys and who likes food? Pop it in the comments. I do. So I'm excited about this session, Mamta. I can't wait to see what you have in store for us. Lots of hellos coming in. So hello to everyone that is commenting as well. And we also have Team STEMette in the comments. So don't worry if we miss a question. We will ask it at the end. There will be time to ask Mamta all of your burning questions right at the end, I promise.
Hi, everyone. I see all those messages. It's so nice.
Someone says they love toys and food, especially food. So
Yes.
house there, Mamta. And we've just popped her social media handles as well. So if you do want to follow Mamta on Twitter and Instagram, we will send this to you after the session. Don't worry, but you can live tweet or live story if you wish. Okay, so as I mentioned, there is a little bit of a food picture there because Mamta did mention food, and Stemettes is all about the food. If you've been to a Stemettes event, you know there's always grub, there's always food at our events. So today is all about engineering and manufacturing of everyday things. So this will all become clear when I hand over to Mamta. Take it away.
So just kind of, I guess this is a good prompt for those people that were commenting. What is engineering? And if you've got a minute, put a couple of comments on what you think is engineering. And the next slide, there'll be a little bit more, just a general view of what engineering is. So give me your thoughts of what you think engineering is about. So shall we go to the next slide and I'll give away some of the things that I think engineering is about. So it's actually a very creative subject. There's lots of designing and problem solving, creating new things and developing ideas and structures and models. It's inventing, you know, you're creating things that have never been done before and never been seen before. So you're really putting together ideas and bits of science and bits of technology to see what can happen. And off the back of that, you're discovering things. You're realizing the way certain mechanisms and processes are put together, and as a result, you're also solving lots of things. Yes, I love that comment. Engineering is fixing things. Indeed, it's all about that. It's all about solving problems and redeveloping things as well. So as you'll see through some of my slides and maybe other engineering talks you've been through, some of these things have been developed and designed before, but we as engineers are trying to make things better and more interesting. So well done, everyone that's given me those amazing comments. Oh, enhancing things. Amazing. I love it. Okay, so that just gives you a quick overview of the E in STEM, so engineering. So what is there to engineer in a toy and in packaging? Now, some of you have probably eaten crisps or a chocolate bar and wondered, is there any engineering in that? And most of you, I'd imagine, have played with toys and think, wow, there's so much engineering in that. So I'm going to go through a talk that talks about packaging and toys. And there's a challenge at the end, so watch out. So within toys and within food, there's loads of things that are involved, particularly in toys. There's lots of electronics, so that is engineering. And there's lots of moving parts. If you can think of like a little train set, we've got to, as engineers, look at how things are molded in bits of plastic and put together. And even within the food industry, there's lots of plastic parts. Even if you think of packaging of boxes, there's also like bits of plastic there. We prototype things, so we test things out, and that involves quite a lot of engineering. And there's lots of mechanisms, particularly within the toy industry, but even if you look at clips within certain types of boxes, of jewelry boxes, or packaging, even like some higher end things like perfume boxes, we've got some really intricate bits of mechanism. Fluid mechanics, so you will see a lot of preschool toys have got bits of fluid, or like you get drinking glasses for children with liquid inside. We have to look at whether the liquid will come out and the dynamics of that liquid. And more than anything, safety and testing is paramount within both sectors, because we need to make sure that the consumer, i.e. you guys and your brothers and sisters and your mums and dads and your guardians, are all okay when they interact with this product. So I'll touch on safety because it's really critical that no one gets hurt when interacting with any of the products. So engineering is so broad. So I hope you enjoy the talk. So I love this picture because it's a little bit like, some of you might feel that when you're planning even like a day out or a party with a friend, in the beginning, it's like loads of ideas. So it's like that messy bit in the beginning, and it's researching venues and researching things to do and budgets. So that's exactly what we do in engineering. We look at the problem, we look at the situation and think, what's our budget? What are our constraints? What's our time scale? And it's all fuzzy and it's all messy. But that's fine, because that's how you plan stuff. You get lots of ideas together. And then as time goes on, you get a concept and you start prototyping it. And that's when it gets slightly further down the curve or the diagram. And then once you've got it spot on and you've tested a few things out, you've trialed a few things, you're smooth as anything. So it kind of goes from this fuzzy to really smooth thing. So I think that's a nice diagram of summing up planning in general. So engineers like to plan. And there's formal ways of planning things. So you might see these diagrams before, like they are sometimes called swim lanes or timelines. Some of them might have used them at school for the older ones in the call, but I use these kind of diagrams regularly, and it helps me plan my projects and my engineering activities. So engineering, I've already touched a little bit on this, but some of the things I've been involved in as an engineer, I've gone to factory audits, I've looked at compliance and quality, so that's related to safety. I've looking at new business partners, so people we can pair up with to make sure that the standard of engineering is of a good standard. It's about engineering and manufacturing, so a very kind of top line. Packaging labels, so a lot of labels that are on bottles or on toys, they have claims, and so we need to know quite a lot about regulatory laws and make sure everyone's safe. Negotiating deals, I've had to read contracts and work with lawyers to make sure that everyone understands what they're buying into, and it is effectively a business deal. Work with retailers, so all the kind of high street shops, make sure they're happy with what they're getting in store. And the fun bit, and the bit that I like the most, is product development. So actually developing something new that will be launched in the market. So the next time you pick up a new toy or a new chocolate bar, think of all the hard work that's gone in behind that. So there's loads of things that go on. And down the side there's just other things that I've done, like testing reports and reworking of things and supply chain management. I mean, it's quite broad, but they're all interconnected, so it's not that scary. So there we go. So this is a little bit of a summary of how to come up with the best product. It's such a simple diagram, but it's great. So it's using really good bits of technology, so things like Bluetooth or flow wrap technology, using your creativity. So all of you, I can imagine, are really, really creative, and engineering. And when you combine those three magic ingredients together, you get a fantastic product. And you might not see it when you pick up your phone, or a nice pen that you like using, or whatever kind of product is dear to you, but all of them have had some level of technology applied to them, some level of engineering, and probably a lot of creativity. So if you can get those three elements and you want to be a cool product designer, make sure that you've got them. So I'm going to talk about packaging and how it's made, and I'll touch on one piece of packaging that I think is really interesting, and I hope you do too. So comment if you think it's a fun bit of packaging. You'll probably look at packaging very differently after this. So I'm going to talk about flow wrap. Now, many of you might have had some bread or a bun in this kind of wrapping. But this is called flow wrap. So I'm going to go through a diagram that explains flow wrap technology. So flow wrap, basically that top piece of the blue circle, spherical piece, that is the big reel of flow wrap. So it's like a big roll of tape, effectively, but it's not always sticky. And then the product goes down a conveyor belt, and then it's literally just crimped on both sides. So that's some really good examples is a standard chocolate bar, everyday chocolate bar. If you look at some of the chocolate bars in the shops, They are made using flow wrap or biscuits, things that need to be mass produced at quite a high speed. And it's literally the wrap flows down the conveyor belt, and that's why it's called flow wrap. So this is some diagrams of the process of flow wrapping. So basically, if we look at the chocolate industry, you get some chocolate, it goes down a conveyor belt, and it lines up the chocolates in a certain way so that the flow wrap is able to allow the flow wrap to go over the chocolate. And any that are slightly misaligned, they just get chucked out and get reused and realigned later on. So if you can think of a big factory, you've got all these chocolate bars going down, they get lined up in nice little rows like little soldiers, and then this wrap goes on top of them. So I think that's on the next slide. Yeah, so this is a bit more technical, but basically that the first picture, and it looks like a little face almost, that machine. The wrap goes on top of the chocolate and it crimps both sides. Sometimes we fill air into them if we want like a bubbly type wrap, and sometimes we take the air out because we don't want the chocolate bar to get exposure to too much air. And I'm sure most of you have seen chocolate bars that look like that silver wrapping. So that's really the simplest example of a flow wrap. I see a comment there about plastic pollution. Yes, it's probably not the most environmentally friendly, but it's one that's used quite a lot in industry. But I'm sure they're thinking of other ways of finding new materials. So I'm going to talk about toys because I think I've worked almost 10 years in the toy industry, and I think all of you can relate to toys. All of you, I'm sure, have played with toys. At some point, you've got siblings or cousins or neighbors that have all played with toys. So I'm going to talk about the serious side of toys. So before we develop a new toy, we look at children's development stages. So you can imagine that when a child is 1 year old, they can only do certain things, and when they're 7 or 8, they're far more established in what they can do because they've just got older, right? So everyone develops at different ages and stages, and so we look at what's called anthropometric data. It's a big, long word. But anthropometric data looks at proportions of hands and feet and heads. As you get older, those proportions all change. So when we're developing a toy, we just make sure that everything is in proportion. So we look at children's development and learning abilities. So that's a diagram out of one of the books, just showing kind of proportions and dimensions, so that we would often use this data to measure equipment and measure new toys to make sure a child can hold it properly or interact with it in the right way. So as a toy engineer, and literally that was my job title for many years, who do we consult? We interact with so many types of people. So we work with designers because they're the really creative people and they come up with the new ideas, but we as engineers make sure that they are feasible and they're doable, because they might come up with something really crazy and we need to make sure that we can actually make it. We consult doctors because doctors often know about things that children are doing, and sadly they might hurt themselves. So we consult them, look at incidences of children that might have injured themselves interacting with toys that were poorly engineered and designed. So we look at that data and make sure that we don't repeat ourselves. Look at child development experts, so psychologists and learning development experts, to see how children are learning and what's the best way of them interacting with things. Focus groups, we get parents, guardians, and children themselves. It was so fun having children come in and work on new development of toys and get their input. The other area is finance, because it's still a business and we still need to make money, but every project has a budget. So making sure that money is correctly spent on different things. Sales and marketing, obviously, because we want to make sure that the shops can sell it and you as a consumer want to buy it. And as a result, the shops and retailers. We look at competitive data because we want to know what else is out there that's going to potentially take our customers away from us. So a bit of competitor analysis is always healthy. I've already touched on incident and complaint data. Recall data is when it actually failed regulations and it was very dangerous. So it's important to look at that. Chemical experts. A lot of toys are made from plastics or other materials that can sadly be quite dangerous if not developed properly. So we consult chemical experts, factory audits to make sure that the product's actually made properly, and test reports because they go to a testing lab and they must pass lots of regulations. And I will touch on that too. So that's just a snapshot of some of the things that I do as a toy engineer. So I'm going to talk about one specific item, and please comment, but who has got a rubber duck in the house or had a rubber duck maybe when they were a bit younger? Because I'm going to talk to you about how a rubber duck is made. It's so exciting. I think this is so fascinating. Oh, I've got a few comments. I've got a rubber duck in the bathroom. Amazing. Okay, let's learn about how a rubber duck's made. Oh, I've even got a picture of a ducky. So I call it ducky and rotor casting because I think it's quite a cute way of referring to little rubber ducks. So little ducky. So there's a lot of data here, but basically the first rubber duck was made from a sticky sap from trees, and this was hundreds of years ago, but things have moved on quite a lot, and we now use plastics, or they're sometimes known as polymers, and it's not a very expensive polymer because they're mass produced, and the plastic is quite strong, it's lightweight, it's durable, and the good thing is it floats, so it doesn't sink because it's hollow inside. And just a bit of history, the rubber duck is a classic iconic in children's culture. And many of you know that. You use them in swimming and just kind of playing with them in the bath. So in summary, they're used as crude oil. I have made from crude oil. And it's similar to petrol. And then we make them in plastic in a factory. And the plastic can then be used into other objects when it's recycled. So there's a bit of a sustainability angle as well. So plastic contains PVCs and a toxic called phthalates. It's now a lot of regulations that are on this about how phthalates are used. So non-toxic chemicals are now used in rubber duckies. And rubber and sulfur were mixed in a stove, and then it became a plastic and are quite elastic. So if you can imagine a rubber ducky, you can kind of pull it a little bit, and that's called its shore hardness for a bit of physics. But it can be quite leathery depending on what type of duck you've got. But the old ones were hollow and didn't float as well. And some of the ducks you may have in the house also squeak because they've got a little squeaker inside. So I'm going to go into a bit of engineering behind the actual current rubber ducks we've got on the market now. So it's a process called rotocasting. So basically it's like a big oven. So that yellow square type thing that you see, that's like a big heated oven, and it's hollow inside and it's got a mold. So the two molds can be taken, the mold can be kind of put into two halves, and you pour in the crude oil or the polymer and it spins around both kind of on two axes. So it goes up and down and it goes round and round, and it just spins and spins. If you think of like a roller coaster ride, right? It just goes everywhere. And it's heated up as well. And then as it cools down, the oil settles at the edges because it's been spinning. It's called centrifugal force. That's another complicated word, but it basically sits on the edges and it solidifies. And when that solidifies, that's why your rubber duck is hollow with a little hole in the underside of it. But basically it settles at the end because it gets cooled down really quickly. So on the next slide, this is a really nice schematic diagram of what happens. So the blue bit is the mold, the plastic goes in, and then the top of the mold goes on. It's spun around really quick at quite a high temperature. And then as it cools down, it just settles at the edges. And then the mold is opened and that generates your little rubber ducky. So here are some other products that you might have in the house or have seen in the shops that are made from rotocasting. So you've got a My Little Pony that I know I've got a few kicking around still, but that's made in the same way. You get a lot of pet toys made in the same way. Preschool, baby toys are made in the same way as a rubber duck. So it's called rotocasting. So if you're interested, have a look on the web about rotocasting. So when we design a product, we need to understand what the product will look like. And before we actually make a rubber ducky, we might want to have it having a bigger beak or bigger eyes or a bigger tail or a smaller body. So whatever we want from this, we have to first model it on a system called CAD, or computer aided design. Has anyone heard of CAD? I'm sure some of you have, some of you haven't, but either way, it doesn't matter. So I'm going to talk to you a little bit about CAD because that's really important when rotocasting any product. So it's a bit of a messy slide, but computer aided design is a software system or computer system that aids the creation, modification, analysis, or optimization of a design. It's a bit full on. But basically, in short, it's about how you get the best design out of a system, because you can edit little bits, you can tweak it, you can send it to experts. So it helps with productivity, it helps designers, so the really creative people help the design engineers, so people like myself see the full potential and they can make it look a little bit nicer, and we can tweak drawings. So we work hand in hand. We can improve the quality. And we can also make sure that we can test it for manufacturing. So
I just wanted to add, Mamta, there was a good comment in the comments that someone had recognised that it was Tinkercad that we were using. So just to double check, is that Tinkercad?
I don't know. I think it is, yeah.
So we had a question on Tinkercad. So well spotted there.
Wow. Someone's very observant. I've never used Tinkercad, but I've used SolidWorks, Rhino, and Pro-E. But they're all kind of similar, but they all have a bit of.
There you go. There we go, girls. Real life of real engineers using Tinkercad. Sorry to interrupt there, ma'am.
That's great. Yeah, so that's a little bit on computer aided design. So you probably know quite a lot if you've been attending other STEMnet talks, but yeah, computer aided design, that is a good example of one. And here's some pictures. So some of you might have seen pictures like this before. So these are engineering drawings or CAD drawings. Yeah, so we use them in all sorts of engineering, so whether it's food or toys, but yeah, these are generated from CAD. And once you have a CAD drawing, you can also do 3D printing, so three-dimensional printing. So we now have very advanced kits. Some of you might even have them in school. I know my old school now has them. They didn't have them when I was at school, but they have them now, which are 3D printers or additive manufacturing. And it's basically when you can produce a product and it's like layers are built up of layers of the product, so you can see what it looks like. And again, this helps engineers and designers visualize what a product will look like before we physically make it. The objects can be almost any shape or any geometry, and are produced by digital modeling data that was made by CAD. And some of you might have heard from AMF files, for those that are maybe a little bit older, but that's a special type of file that a lot of these CAD drawings generate to produce 3D prints. So here's a whole list of different 3D printing techniques, and I'm just going to touch on one of them, which is on the next page. But literally, if you go on to Wikipedia and look at 3D printing, there's quite a lot of information on it. It's a fascinating area. It's really, really interesting. So it's called selective laser sintering, SLS. I don't know if any of you have heard of it, but it's really interesting to watch. And it's 3D printing. It's a type of AM technique, additive manufacturing. And it's called that because you're adding on layers after layers after layers. And it uses lasers as well. And basically, you aim the laser and it does it automatically. It's all programmed at different parts, and it binds the material together to form a solid structure. And it's similar to directing a laser at metal, where it zaps the metal into a technical shape. So it's really good for modeling, and it's quite a well-known method. I've used it quite a lot. So if you find that interesting, do have a look at that, because it's what's used in industry and probably in your skills as well. I'm also going to touch on magnets. So shout out if anyone has got any magnets in the house, or your fridge, in your pencil case, or anything like that. I know I've got some magnets in the house, but magnets can be really interesting, but they can be also very dangerous, particularly in toys. So I'm not going to scare you, but I want to just highlight some interesting facts about magnets. So here are some toys that you may have seen that have magnets. So that kind of spirally thing, I've still got that in my house, but I loved that as a child. It was so interesting. And then you get the alphabet magnets. You get these kind of cube things that you can join up. You've got an Etch-a-Sketch type product that uses magnets, believe it or not. And this is a construction set using magnets. So post some comments if you have got any toys with magnets, or know of any other toys that have got magnets. This is just a few that I thought of. So I'm going to talk to you about button batteries as well. So I'm going to talk about magnets and button batteries, but magnets. So toy engineers, when they're looking at the quality and safety, there's 3 or 4 things that they need to watch out for, really, that's really dangerous. So small parts, and when you were all really little, you probably put things in your mouth or in your ear. So we need to watch out for small parts. We need to watch out for batteries, because they can be quite dangerous, particularly the smaller ones, and magnets. And I'll touch on some of that. Some of the other areas that are quite dangerous are sharp edges, because when you're little, you can walk into sharp edges, like the edge of tables. So there's a lot of research into toy development that reduces the sharp edges. So you'll see in some of the preschool toys, all the edges have been rounded off just to make them a little bit easier so people don't hurt themselves. Chemical testing, microbiological issues, so making sure like fungus doesn't grow in things, entrapment issues, so arms and legs don't get stuck, and that is just a few of them. So on the next slide, I'll go into details of a magnet. So most of you will know, or might know, that a magnet is a type of material that's got a magnetic field. So it's a special type of, it's got special properties, and it basically has a pulling force. And that pulling force is called the north and the south poles. So it pulls or it attracts, right? So it either pulls or attracts. And it can be used for all sorts, and it has been proven by experiments that, you know, the magnetic poles either repel or attract one another. So what is a magnetic field? You know, let me know if you know. but basically it's a space that surrounds the magnet. So you can't visually see it, but on a piece of magnet, there's actually a field that goes around it. And if a bar of a magnet is placed in this field, it will exert a force, and that field will either remove or attract the magnet. So that's why magnets are quite interesting bits of technology or whatever. So the bad thing about magnets, if not done properly, is if you swallow a magnet, and please do not try this at home. It's incredibly silly and incredibly dangerous. But magnets for children's products tend to be quite weak because they can be quite dangerous if inside the body, and you can get hospitalized. So there's a rule within the toy industry that magnets have got to have a flux value of less than 50 kg squared per millimeter squared. So it's actually quite a weak magnet, and it's such a weak magnet that it shouldn't be dangerous. But if it's anything more than that, it can be quite dangerous, particularly for children under the age of 3. And it's also got to be quite a large size. So there's a gauge that we use within the industry to make sure that the child cannot put a magnet into their body. So be mindful of magnets. They're actually quite dangerous. And this is what we use to check for choking hazards. And this is a proper test. This is a little gauge, and I had quite a few of them. But basically, if you can put an item into this gauge, and it's like it's like a little cylinder, and if you can put a magnet inside there or any object in there, it's basically an indication that it could be a choking hazard to a child. So that's a big piece of important piece of work within the toy industry, because it makes sure toys are safe. So the regulations within the toy industry is called EN 71, and if you go on Google, you can get lots of information on EN 71, and it's a European toy standard. The American equivalent is ASTM F963. It's slightly different, but they're like the technical regulations. And it ensures that toys are made for children that are safe and apply to all the standards. So we look at incident data, we look at what doctors are saying, we look at all the things that can make a toy safe. And in some countries, they must fulfill multiple standards. And if there's no regulations, so some countries don't have any regulations, they might follow the European standard or they might follow the US standard. But they really do make sure that toys are as safe as possible and not dangerous. So that little line at the bottom, the danger is often not due to the design, so us design engineers, but usage of maybe just not used correctly or properly. So we need to look at how a product can be misused as well. So that's a bit of a scary part about toys. So I've whizzed through so much stuff, and I hope that was interesting. So let me know. But I've now got a quiz for you. So I don't know if Charlotte wants to take this, or if I want to.
Yeah, I just wanted to give you all like a virtual clap, actually, a real virtual clap from everyone else that is tuned in on YouTube. Because I feel like I've learned so much about the engineering of the rubber duck and toys in general. I found that fascinating. I think pop in the comments if you enjoyed that, if you found that fascinating. We have got a little quiz, as Mamta mentioned. Mamta, I hope you enjoyed that as well.
It was really good. Sorry, I felt like I could talk about it for hours, so I'm careful that I might bore people, but I hope it was fun.
We've got a couple of clap emojis coming in there and things that are along. Thank you so much. This isn't the last we've heard of you anyway. So like you said, we're going to do a quick quiz. Then there were loads of questions that came in as you were speaking, Mamta, because the girls were, of course, really engaged. If you want to grab a piece of paper, or if you don't want to, you want to just do this from memory. Mamta, what's the first question?
Okay, drum roll. What do you call the method to make a rubber duck?
Okay, so if you were listening, Mamta mentioned it a few times. So pop your answers in the comments. And then the second question.
Okay, I went through a few of these, but name 3 things toy engineers must watch out for the safety of children. So I mentioned 3 or 4 really key things, but there's lots of other ones. So can you think of 3 things that you think as an engineer I must watch out for if I'm going to design a new toy?
Very good question. So that was the most recent module that you just covered just there, actually, Mamta. So hopefully they were listening right to the end. So folks, yeah, pop your answers in the comments. I can see your answers coming through. We'll ask one more question, and that is what, Mamta?
It is, what does CAD stand for? Oh, do you remember from the presentation what CAD stood for? I'm not, it's a difficult one.
So for those that did join our Tinkercad session a couple of weeks ago, hopefully it's stuck in your brain. You've remembered as well as from Mamta's presentation. So do we want to go through some of these comments and see if anyone's got the answers right there, Mamta?
Yeah, let's do that.
Go for it. So if you want to call out any names or any answers that you can see with really good answers.
Let's see. Oh, here, wow, we've got loads of answers. Oh my God, okay, let's start. Wow. So where do the answers start? So C is computer-aided design. Well done, Moha. I think that's how you say your name. Glad Williams, she said rotocasting. Yes, that's how a rubber duck is made. So well done, amazing. Elizabetha, you've got all 3. Amazing. You've been paying attention clearly. So yeah, rotocasting was how a rubber duck's made. Magnets, sharp edges, and choking are 3 things that you must watch out for when designing toys. And CAD is computer-aided design. Tulu, yes, Ducky and rotocasting. Yeah, amazing. The title of the presentation. What else have we got? Aliyah, rotocasting. Yes, well done. Sawila, I can't say your name very well, sorry. But magnets, yes, magnets are really dangerous if not designed well. And you've also said choking and sharp edges. Yes, well done. Karina, yeah, you're spot on. Sharp, small parts, batteries, magnets. Oh wow, you've gone to town there, and you've also got chemicals. Yes. Oh my God. Really pretty people here. My gosh, budding engineers for sure.
There you go. So there you go. As you read out, Mamta, those are some examples and answers to the questions. So well done to everybody for getting that right. For getting, I think everyone was listening and engaged in your presentation. So thumbs up.
Oh, amazing. I hope it's sparked you thinking about things slightly differently. So I've got a bit of a challenge as well. So now you've got the answers. First question. Let's do questions.
We'll set that challenge, a little bit of homework for everybody. So we've got a couple of burning questions. So we're at 1:45 now. So we're going to go up for another 15 minutes. So we'll have questions, then we'll do the challenge, then we'll do the feedback, and then we will close up. So I know Soraya had a burning question, so that's on the screen now. And it is, what is the craziest toy idea people have had so far, Mamta?
Oh my God. I did a session at the Institution of Engineering Technologies, and I asked children to come up with the coolest or the craziest, however you want to say it, toy idea. And I love some of the ideas they came up with. So somebody had like a giraffe that morphed into a car. I thought that was really fun. And this little girl, she loved dancing. I love dancing and I love music. So we came up with, this was a joint thing, we came up with dancing shoes that you put on and they would teach you how to dance. I love that. I still want to see it. I know, it was like a market success. So I think they were some of the best ones I've seen so far.
That is such a good question. Thank you very much, Soraya, for that question. Julia, if you want to pop up another question that was asked. So we'll get through as many as we can, or we can pop them in the comments as well. So pop your question if you do have a burning question. I do like those crazy ideas, Mamta. I want a pair of those dancing shoes. First in line for that when we can get out and dance, of course. We've got a question here from Isabella. When you factor in fluid dynamics, do you use the Navier-Stokes equations or are they used more in maths and physics? That's a technical question for you.
I'm stuck. I don't know what the Navier-Stokes equation is. Oh my goodness, you're very wizzy. I probably would leave that to the really technical engineers. I'm more of the designer person that comes up with and helps the designer. So good on you. But I use fairly everyday physics and maths, manufacturing techniques. So I think you've got me there.
Don't worry, Isabella. Maybe we can do a bit of digging, find out for you, Mamta. Maybe we can answer that. Don't worry, we'll put you an email if we have anything further for that one. So lots more questions we've got coming through. So Glad asks, what university did you go to, Mamta?
Yeah, so as some of you might be able to tell, I've got a bit of a Scottish edge to my accent. So I grew up in Scotland, and I did my undergraduate at Glasgow University, which was actually the university that some of you might know because Lord Kelvin went to there, and James Watts, some really well-known engineers and physicists and scientists. So it's quite an old university. So I did my undergraduate there. I then did a master's in engineering from Strathclyde. So I studied up north, and then I moved down south to get my first job.
So you stayed in Scotland for your education then?
Yeah, because back in the day it was free, right?
True. I would have stayed as well. This is true.
And I could live at home, which was quite nice to see.
Of course.
I felt a bit young to move away from home back then.
So I've got another question here from Alexandra who asks, what is your favorite CAD program and why?
It's probably SolidWorks because it's the one I know the best. It's the one I got trained in at university and then used in industry. I'm not so good at Pro E or Rhino, but I think SolidWorks, as much as I don't use CAD as much now, I find that's gives me a lot of flexibility, but most of them are much of like, once you know one, you can adapt quite quickly to others.
Cool. Great question there. And Ayla asks, is your job hard?
I like to think so. I make everyone tell it. Is it hard? I think like skills quite hard. Like everything is difficult, but equally if you enjoy it and you like it, and you have like good people around you and you're passionate, like some people find STEM quite hard, but if you're genuinely interested, you will kind of try and persevere and keep at it. So I think my job can be quite challenging because like sometimes we don't know what's going to come our way and it's very unpredictable. But in that way, I actually find it quite interesting because I like a new challenge. So.
There's that saying, isn't it? If you do a job you love, you never really have to work a day, right? So
I wouldn't go as far as saying I love it though.
Well, we love toys, so we love that element. So Evelyn asked, how long does it take to design something?
That's a really good question. It can vary. We can take, if it's a really simple adaptation, so say maybe like making a rubber duck from yellow to blue, that's quite a simple product change, or putting spots on it or stripes on it. And so that can just take a few months, right? It's just a simple bit of adaptation. But if you're developing a brand new toy and you've got teams from the States and from Europe and maybe confidential stuff, so maybe a film based on a film, so we can't always get access to all the drawings because it's all kind of private data. It can take up to a year. And sometimes even longer if you need to negotiate with suppliers. But I would say 6 to 12 months is the standard kind of what we call a lead time. So the time it takes from beginning to end or beginning to launch or first production. Yeah.
There you go. It takes up to a year for those toys that you're playing with. So good to know that it doesn't just happen overnight, eh? So we've got time for a couple more questions. We've got a question here from Daniel. Have you 3D printed before? And if you have, what did you print?
Yes. So I'm kind of a little bit away from the CAD side in my current job. But when I was at university and also as a junior design engineer, I used a lot of CAD. So the very first thing that I used CAD for properly and actually got a CAD physical piece from, and it was amazing, was I developed a diabetic blood tester for my final year project at university. My mum's diabetic, and I just wanted to develop something that was better and easier to use. And it won a couple of awards because of how I made it. So yeah, I was really proud of that. I was like 21 or something, and I got the 3D model, and it's still sitting up in Scotland. But yeah, it's this model, and it's got all these different components and parts. Very difficult, and I don't think I'd be able to do it now because I've forgotten all those skills. But that was my first piece. But then in industry, I used it to make little pieces that for toys and things like that. So sometimes in CAD, we will make a CAD drawing like 10 times the size that it should be. So if you think of like a piece, a little model that goes around a board game, we'll make that 10 times the size and print it off at 10 times the size. So it's like this size opposed to this size, because it then means when we shrink down the artwork and the drawing, we get all the detail, and we can really see it when it's big. We can make sure that we get all the detail. So it's really nice seeing these big models.
Giant. Make it giant, then you make it normal size.
Yeah.
Cool. So I guess related to COVID, are you back to work? What's the current stitch now?
So I'm working from home. So this is my living room that you see here, and I've been working from home since kind of lockdown. And yeah, I've got my laptop, I've got my desk, I've got my coffee, I've got my juice. Yeah, so I've been working from home, and we've been doing lots of video calls and things like that. So managing to get back, actually.
There you go, folks. You can be an engineer from your very own living room. Right there.
I have a yoga mat here as well. It's like,
and you can be a yoga. So maybe the last question now. So we're just coming up to a close, and Tolu asks, "What is the best toy you've ever made so far?"
Oh my god, so much oh, so many toys over the years. I've worked on things like Action Man, My Little Pony. I've developed slime. That was amazing working with quirky scientists. But I think the first toy that I've ever worked on was like my favorite. I was a really junior engineer, and I had I worked on a Monopoly board. So most of you have probably played Monopoly. And there's lots of different versions, and I worked on a Lord of the Rings Monopoly, and it was just so exciting at that young age to work with Hollywood on these amazing pieces that were like really high end. I think like the board sold for like £35. It's like a premium product. And yeah, so that's probably my favorite because it was my first one. But I've done all sorts of, from dolls to
cool.
Yeah.
Very, very cool. So lots of people in the comments, lots of the everyone kind of saying cool and ooh and wow. So yeah, I think we do have time for one more. And Isabella says, what are the best and worst parts of your job? That is an excellent question, Isabella. Maybe one best and one worst to keep it nice and brief.
Yeah, so one best, I like the fact that I design stuff and engineer stuff, and then I can go in the shop 6 months later and go, I knew all about that well before everyone.
So cool, like an insider. I love that. And then the worst, if there is anything?
I think it can be really unpredictable. So you can work on things for months upon months, and then you find that the trends have changed or the movie's cancelled. So yeah, you can put a lot of time and effort in something and then never see it come to market. So that's quite sad.
Oh, well, that concludes the Q&A. So thank you to everybody, and thank you so much, Mamta. I know you want to set a little challenge, a little homework maybe?
Sorry?
I know you wanted to set this little challenge, or maybe a little homework challenge for the
yeah. So I guess we went through quite a whizzy talk, but if you get time, and no pressure, but if you get time, look around the house, and if you're allowed to pop to the shops, but there's probably lots of things around the house. Take some pictures or just write them down. 3 things that have got flow wrap. You'll probably find some things, here's a hint, in the kitchen or kind of cosmetics maybe. But lots of food items tend to be flow wrapped. And look at 3 objects in the house that are rotocasted. So if you've got the rubber duck, you've got 1. I need another 2. See if you can find them. and 3 things in the house or out and about that have got magnets.
Okay, I like that. It's kind of like a treasure hunt with no pressure.
You might find that here's a big challenge. If you can find an item that's got all 3. I don't know if that's possible, but let's see.
Oh, okay, all 3 in 1. There you go. Challenge accepted. So that is also, it says in the bottom here, show us your findings by tweeting photos and tagging at STEMettes or MAMTA Single 2 with STEM mode in hashtag.
Yeah, so, Instagram as well. My Instagram as well.
True. So we did have your Instagram right at the beginning, but don't worry, we will follow up after this session with all the things that we've mentioned, all the things that you need to know, all the hashtags and all the handles for you there, MAMTA. So I'm looking forward to seeing some of those and the findings that we get from that. So the last thing that I'll say to everyone, of course, if you have been attending our sessions, is for feedback. So remember, you will get a certificate. So we'll ping those electronic certificates to you next week to say that you have participated in this incredible session, this incredible engineering session by MAMTA. So we will ping that to you once you've done that feedback. Let us know what you thought of it, how much fun you had, any sort of comments. We'll make sure we pass that on to you as well, MAMTA. So that's a link there. Scribble it down, take a screenshot, write it down, whatever you'd like to do. So it's bit.ly/STEM Wednesday 11. Gosh, we're in week 11 of STEM mode in. Almost at the end there. But MAMTA, it's been an absolute pleasure. I hope you've enjoyed it as much as we have.
Loved it. It's lovely seeing all the comments. It's been brilliant.
Brilliant.
Such great people out there.
Yes, agreed. Some of the questions blew me away. So yeah, well done to everybody. The comments, the questions. Soraya's already done the feedback. Just going through any comments. Thank you very much for doing the feedback. Don't worry, we'll make sure we get those certificates to you. And don't forget, we are going to put you, so for everyone that's done the feedback forms across the 11 weeks, we'll pop you all into a prize draw to win a prize at the end. So at the end of week 13, so there's 2 more weeks left of STEM mode in. So you'll be popped into a prize draw and who knows what you could win. And draw. So there's lots of incentives to fill in that feedback, and we will share that with you, of course, as well, MAMTA, to let everyone, so everyone you can see how much fun everyone had.
I look forward to it.
Cool. So I think without further ado, do make sure you join us in the society. So if you are age 13 and above, we do have a closed network called the STEMettes Society. So where you can sign up to these events first. We've got lots of opportunities on there. A whole wealth of knowledge is on there, and everyone kind of shares and collaborates stories and shares their wins as well. So do join us on the society. The link is on the screen. And of course, on all social media, you'll see us tweeting and posting furiously for the next couple of days, MAMTA, with your face all over it, I'm sure. The incredible slides and of course the incredible session. So next week, so I've just got a prompt here. So next week we are creating a game with a company called Buildbox. That is very true. So it is Ada Lovelace week. So if you want to create a game with a company called Buildbox, join us next week. It's going to be a good one.
I so want to join.
And then this Friday, of course, we have our Friday lives. So do join us on Instagram if you can, if you like. It is all about entrepreneurship with a lady called Lola and a lady called Anissa. So do tune in at 4 p.m. on our Instagram if you have Instagram. So much, MAMTA. We're doing so much and so little time. And we have incredible people like you joining us for STEM Mode In. So thank you again. So without further ado, I think we are at the end. So right on time. There you go. Slap bang an hour. MAMTA, is there anything else you'd like to say to close off?
No, but thank you for attending. Keep attending these things. I know when some of you go back to school, but keep following STEMnets. And if there's any bits in the presentation that you're not sure about or want to know more about, there's feel free to reach out to me or STEMnets or at your teachers, or go on Google. There's lots of stuff out there, but I just think it's super fascinating. I've done this job for now 18 years and I can't get enough of it. So I hope you enjoyed it as much as I did.
Oh, amazing. Thank you so much, MAMTA. And there's one question in the comments here that said what age. As long as you have an Instagram account. You're allowed to have an Instagram account. You can be any age. So we have all different ages. So do join us there. Thank you again, Mamta. See you all soon, everybody. Bye.
Bye.